Welcome to Obhi's Math e-Pathshala.
So today my lecture will be on the concept of group action of a set, uh, group action on a set uh, where a group acts on that set. So what does it mean? Now see, first of all I would like to uh, give you an example where you have already done such group actions. Suppose if you are in a plane, so in 2D geometry you have already do some translation and rotation uh, concepts. That is, if we just uh, consider a point xy, and then we consider another point x dash y dash. Yeah. Then what is our uh, process to send this point xy to this one? What is the process? The process is to rotate the line segment joining 0 0 and xy to the point x dash y dash by specifying a rotation matrix. That is, if you have a rotation matrix this one, so cos theta sin theta minus sin theta cos theta of, if we uh, regard this point as a column vector, xy goes to x dash y dash. Okay. So then we shall get the new point will be x cos theta plus y sin theta and y dash is minus x sin theta plus y cos theta. Yeah. So this means that these matrix act on this point, and after the action has been taken place, this point map to x dash y dash. So that is an example of a group action, a particular one. Now we shall define now we shall define in general by considering a group and a set. Now we see that in that example the set is the plane R2 and the group was the set of all those 2 cross 2 orthogonal matrices over the field of reals. So that is the group. Now in general we shall define, so in general we shall define that first of all we consider a group and suppose X be any set. So in that example X is R2 and the group is O2R, that is the set of all those orthogonal matrices over the field of reals. So let G be a group, X be any set, then what is the meaning of action of the group on the set X? Then a map which is denoted by dot colon G cross X, that is we are considering the Cartesian product of the group with the set X, and where it will map? It will map to the set X. So X is the codomain of this map. So let X be, let G be any group, X be any set, and if we consider a map dot G from G cross X to X denoted by, how do I represent this? Just taking one point from the group G, another element from the set X, just putting dot here, then G dot X will be the image of this one. Excuse me. Denoted by dot of this. Yeah. So dot of G comma X is a point in this G cross X. Then this map will take this point to this one. This is the notation of the image of that map at this point, G dot X is called a left action of G on X. If why we are calling it left action? Because the group acts on X from the left, G cross X. If we are considering the right action, then this map will be X cross G to X. That is, the group will act from right. So this is called the left action of G on X if the first condition is for any two elements from the group G1, G2 belongs to G, and for all X belongs to X, if G1, G2 dot X equals to G1 dot G2 dot X. Yeah. If this condition has been satisfied by this map, this one is G1, G2, that is, here we have the binary operation induced in G, and this is the map, this is the action we are considering. So G1, G2 dot X will be G1 dot G2 dot X. Don't regard this as an associative property, because this is a set only. This is not associativity. Never think that this is associativity. This is not associativity. This means that g1 g2 dot x is g1 dot g2 dot x. This is the action. And the second condition is, since the group has an identity, so this identity will act on every x and it will give small x for all x belongs to capital X. That is, E dot x will be x. That is, if the identity will act on the set, it will give the same element. Just look at the example we have already considered. Here, if you are considering the identity matrix 1001, then it will uh, just by matrix multiplication we will have ixy equals to xy. So here the action is the multiplication, matrix multiplication. Okay. So this map will be called left action of G on X if these two conditions will be satisfied by this map. And in that case, if such a map exists, then X is called the set is called G set. Whenever we are uh, considering a G set, that means the group G act on the set X by some left action. Now, if we are considering right action, then we will specify that this action is right. So, in a similar way, we can define the right action of G on the set X, and that will be in the same manner. So, right action means that is dot is called from x cross G to x is called a right action on G if the first condition will be, now here the first condition is this, then what will be the first condition for this right action? That is x dot G1 G2. So this will be x dot G1 dot G2. And the second condition will be x dot E equals to x for all x belongs to capital X. Okay. Now, some examples are there where you are compelled to define right action. Naturally, it will come. The action is right. Okay. Now, let us have a look on some examples. Now, the first example is uh, very much easier. That is, just consider a group G and let us suppose that H be a subgroup of G. Okay. So let G be a group and H be a subgroup of G. Then we consider the set. What is the set? X is the set of all left cosets of H in G, which can be denoted as H slash H, G slash H. So we consider this set, that is the set of all left cosets of H in G. Now we define a left action, define a map dot colon G cross X, G cross X to X by. Now taking one element from the group G and one element from the set X, that is X is the set of all left cosets. So consider a left coset, suppose AH. So the definition will be G dot AH is which left coset? GAH. G dot AH will go to the left coset GAH. So this is the definition of the map. Now we will check that does it satisfy 1 and 2. Now suppose for the 1 we consider two elements from the group G, G1, G2. Then G1, G2 dot H, it will be G1, G2 H, H. That is now this one. Now since G1, G2A, these are all elements of the group G, so they will satisfy associativity. So that means it is G1, G2A, H. That is, it is G1 dot G2A H. That is G1 dot, now G2A H is G2 dot H. So this shows that condition 1 is satisfied. Now for condition 2, the identity of the group is E, then E dot H goes to EAH, that is AH, and this is true for all AH belongs to X. So this proves that the map dot satisfies both the conditions 1 and 2. So therefore this map is a left action of G to X. Okay. Now I forgot to tell you that yes, if X is called a G set and we will say that G acts on X from left. G acts on X from left. This is the language we will use. Okay. So this is the first example we may consider. Okay, and the second one will be now if you consider the right cosets, then what will happen? Let G be a group and H be a subgroup of G. We consider the set X equal to the set of all right cosets of H in G. the set of all right cosets of H in G. Then what to do? Then we define a map dot from. Now the natural way to define an action on X is to consider a right action, because so we are considering a map from X cross G to X by the rule HA dot G will be HAG. Okay, HA dot G will be HAG, this one. Now if you consider the left action, suppose G dot H, G dot HA, sorry, G dot HA, then you cannot copy the same definition from the left action you have defined for the left cosets of H in G, because in that case this will not give you the result, because this action will not be the left action, because if you define this G dot HA is HGA, then what will be G1 G2 dot HA, that is H G1 G2A. Then is it a left action? Okay, so H, yeah, so just putting the associativity here, yeah, so yes, so this one is G1 dot H, yeah, okay, G2A, right. So G1 dot so this is again G2 dot HA, yes, yeah, okay. So this action is a left action, and now if we consider the second case, then it will be HEA. Okay, so this is HA. Yeah, so this action, this definition is a left action, yes, for this one. And now what we have considered, so HA G1 G2, then HA G1 G2 bracket. So now if we apply the associativity, then it will have, so A G1 G2, so it is H A G1 dot G2, and it is H A dot G1 dot G2, yes. And also for the identity, it will be HAE, so it is HA. So this action is right action. So this is a right action of G on X. And also we can consider this action which is from left. This is a left action, but you need to define in this way. You cannot define, suppose, okay, let us check if we consider the map dot colon G cross X to X, where X is the set of all right cosets of H in G, by G dot HA equal to H AG, the same image as we have defined in the right action. Then what will happen? Then G1, G2, let us check what will happen. HA, G1, G2 dot HA, then it will be HA, G1, G2. And then you consider the associativity, so it will be H A G1 G2. Then, so now for this one, it must be G dot G2 dot H A G1. Yeah, AG1, and this is equal to, now what is HAG1? So it will be G1 dot HA. So thus this fails to hold, because G1 G2 dot HA must be equal to G1 dot G2 dot HA, but in that case it get reversed, that is G2 dot G1 dot HA. So this map is not, so this map will not be a left action. Left action of G on X. So this is an example of a map which is not a left action. But if you define this way, G dot HA is HGA, then it works. That we have seen that, yes, it satisfies both the properties, both the axioms. Sorry. Now, let us recall the example that we have written down at the beginning, that number 3. So let us consider the group G is GL2R. What is GL2R? It is the group of all 2 cross 2 non-singular matrices with entries from R, real entries. And what is the set? The set of all 2 cross 2 non-singular matrices with real entries. This is the group. And what is the set? The set is the plane R2. Then we define a map dot from the group G, that is GL2R, cross the set X. What is X? X is R2. So it is R2 to the set R2. By the rule, that is, we are considering a matrix from this group, suppose A, capital A, and let us consider the elements of R2 as column vectors. So then we have, so A dot xy. So A dot xy goes to the matrix multiplication of A with the column vector xy. So this is your action. Now we shall check that if we consider 2 matrices AB, then what will happen? Then AB dot xy is AB multiplied with xy. Now since this matrix multiplication is associative, so it will be A B xy, that is A dot bxy, and that means A dot B dot xy. And for the identity matrix I, dot xy. So it will be xy. So hence this map satisfies the axioms of left action. So hence dot represents a left action of GL to R to R2. In a similar way, you can consider the group of all 2 cross 2 orthogonal matrices with real entries. In a similar way, yeah. Now, let us have a look on another example in general in a group. So, let G be a group and N be a normal subgroup of G. Normal subgroup of G. And then we define, with the help of this normality of the subgroup N, so we define a map dot colon. So this is your set and G is your group. So dot colon G cross N to N. So dot is a map from G cross N to N. That is, we are to consider the group G, which will be acted on the normal subgroup N. So the definition is that, so dot colon G cross N to N will be defined by, so taking one element from the group G and another element from the subgroup N. So G dot N. What will be G dot N? The natural choice of the image is this Gn G inverse. As because in a normal subgroup we know that for every element small g belongs to the group, and for every n belongs to the subgroup, Gn G inverse will be an element of the normal subgroup. And since n is normal, this element belongs to n. So this map is well defined. Now we need to check the axioms 1 and 2 of the left action. So for this, let G1, G2 be two element of G. Then G1, G2 dot n. What will be that? So G1, G2 n G1, G2 inverse equals to G1 G2 n. Now G1 G2 inverse is G2 inverse G1, that is G2 inverse and it is G1 inverse. So G1 of, so G2 n G2 inverse means G2 dot n G1 inverse, and then it is G1 dot G2 dot n. So this satisfies the first axiom. Now for the identity E dot n is En E inverse, which is n, and this is true for all n belongs to the subgroup n. So hence, so dot is a left action of G on the normal subgroup n. So this is another example of a left action. Now, during the discussion, we shall consider more examples. Now we move to view this group action as group as a group homomorphism from the group G into the group of permutations. So this can be viewed as an homomorphism, from the group that we have considered from G to the group of permutations. Okay. So let us have a look on this discussion. So the theorem is that let X be a G set. So X be a G set means you have already in your hand a left action of G which acts on X. Then the left action of dot of G acts on X will induce a group homomorphism from the group G into the group of permutations curly AX. So into the group of permutations curly AX of X. So thus this theorem says that the left action of G which acts on X can be viewed as a group homomorphism from the group G into the permutation group defined on the set X. So that means for any group action you can have a group homomorphism from G into the permutation group of X, that is curly X. And in the reverse case, if you are considering a group homomorphism from G into the permutation group curly AX of a set X, then it will definitely give you a left action. So let us have a look on the proof of this theorem, how to define the group homomorphism. So that is our aim, using the.
Thanks for watching.